This talk. You hear me? Yeah. Okay. I'm Michele Caini. Thank you for being here. I know the other talk is quite good, but you are here anyway, so thank you. This talk is about entity component system. It won't be, I won't try to tell you that this is the best thing that can happen to you in your life and you can do anything without it or nothing like that. Even though most of the talks about entity component system tries to convince people that they have to use it or load their software. And this talk won't be about entity. If someone has this expectation, so I'm sorry. Entity is a library I wrote, and is also the reason for which I studied a lot about this topic, and for which I decided to make a talk about entity component system. Thank you to our sponsor, host, and all the others. So first of all, what is an entity component system? It's an architectural pattern. It's mainly used in game programming. At least I met it mainly in game programming, also in some other areas, but mostly related to rendering stuff. So I've seen it used as an example by ECS and their rendering engine for their software, things like this. Usually people, to explain how does it work, so what's the idea behind this pattern, showing an image where there is a key that is an entity in theory and has some component, and system is as some other component, and the key unlocks the system only if the components match. And this doesn't make much sense to me, so I usually try to explain how does it work, how it works using this image. And the basic idea is that it's an approach slightly different from what is object-oriented stuff. If you consider the object-oriented approach, we have, as an example, a hierarchy of objectives. Imagine a game, so a hierarchy where you have, I don't know, your game object, that is the base class for everything, and simplifying everything, the best. You have an update member function in this object that is a virtual member function, and you can imagine that you have an array where you put all of your objects, so hero, orc, wolf, and mountain, and also all the other objects. And when you want to update your game, you start iterating this array, so this vector, and invoke update on each game object. So if you look at this image, when you invoke update on your hero, you don't know it's an hero, actually, but you want to update it, and it start updating its input, so working with its inputs, so doing something if the user presses the button or something like that, updates its position, updates the velocity, and do what is required to draw itself on screen. Then you pass to the orc, and you invoke update, and all these blocks, you can imagine them as if they are functions. So the update internally invokes all the functions required to update the object as a whole. Entity component system tries to flip the problem on its head and say, okay, if you want to update the position of something, so of an object, you have somewhere in your hierarchy a position and a velocity, so data members for position and velocity. And a function, and a function that uses this data, so uses the velocity and the position to update the position. Okay, try to do that. Get this logic, so this function, and move it out from your hierarchy. So in a free function, if you can, or another class that isn't part of your hierarchy, and that's your system. So your system are usually plain function that has only a goal that they do only a small piece of logic of your software. Then get your data members, so position and velocity, and define struct, so classes with this data. So one or two classes for position and velocity. So for movement, you can also define only one struct, and these are your component. So we have system, we have component, and what are our entities? Your game object now become your entities. What does it mean? It means that usually entities are numbers or numerical identifiers, and you literally attach components to entities. So your hero in the entity component system pattern is no longer an object, but is a number, is identified by a number, to which you know is attached some component, in particular input receiver, position, velocity, and sprite somewhere. You don't know where, at least you know where, otherwise it won't work. But it doesn't matter at this point of the talk. Your system, when you want to execute, just query the registry or the component manager or whatever is the name. Usually components are stored directly within the system, and so system query each other. But this is implementation details, so it doesn't matter here. When a system wants to update something, it says, okay, give me all the entities that have at least these components. So movement system makes a query and say, okay, give me all the entities that have at least components, position and velocity. He obtains the list of entities and the list of components, obviously, and start updating all the position based on position and components. So it's a way of looking at your data and so this sprite, velocity, and position are no longer function as in the classical object-oriented approach, but are now pure data. Usually in a pure entity component system approach, components are pure data, there's no member functions at all, and all the logic is in system, within the systems. So the idea is that now you have no longer a hierarchy, and why should I do that? This is the first question that people usually do when you try to explain this approach. The basic idea is that, first of all, code organization. It's really, really easy to add and remove features, new functionalities to a software. If you think of a game where you start developing this game and usually you have an idea, but you don't know exactly what you're going to do, what you're going to do in details, and things can change during the development of the software. Having a method to add and remove features without completely destroying the code base is something that can help quite a lot. And here, if I want to add a new features, I just have to add a new component and a new system. And all the logic, I have no longer hierarchies, I have no subtle errors that can pop out from some method I want to change, because a new features means a new component, or one or more new components, and a new system. And all the other systems continue to receive all the entities with which they were working before I added this new component, this new system. So code organization is one of the main reasons, because it's really easy to extend the software this way. Obviously, it works quite fine when your objects are overlap quite a lot, because obviously this works fine because in a typical game, typically you have that more or less all the objects have a position, can move, you can draw them, and so on. So the objects overlap quite a lot, and this is usually one of the requirements for which you can start thinking to an entity component system. The other reason for which usually people start doing something like this, and I'm not sure you know that, but nowadays this pattern is a trending topic, because Unity introduced something similar in its engine, so it's a really trending topic, and everybody is talking about this. And I started studying this stuff 4 or 5 years ago, so I explored a different implementation. Another reason for which we want to do this is performance. Because before you have objects all around, so when you start updating things, you update one thing that is here in memory, another thing that is here in memory, and you trash your cache almost continuously. So get your data from memory here, get your data from memory here, and so on. And you have not a cache-friendly approach to the problem. This way, instead, you don't have a cache-friendly approach, a cache-friendly solution, but you can have a cache-friendly solution. So it can be, you can push these towards a cache-friendly model. It depends on the implementation. There are some implementation, and I'll show you one of them that is probably one of the most used in the C++ community that isn't cache-friendly, in fact. It's quite incredible, but it was on GitHub in 2008 or something like that. So it was the only one, and almost everybody started using it. But it's not cache-friendly at all. But you can get a great improvement in terms of performance. Because imagine the rendering system starts iterating over sprite. Imagine you have all your sprites put in a vector, so in an array, and you're iterating your array from 0 to n. So you cannot imagine something better than this, because you get the first element, all what arrives from the memory is something you're going to use immediately after the first element. So this is quite good for the cache. The cache is going to, yeah, thank you. This is something like big warning, because almost everybody today makes a talk, almost everybody, well, there are a lot of people today that wants to, because of Unity and the trending topic, wants to make a talk about this topic and say, okay, use it, use this pattern, and everything, you'll solve everything, you won't have any problem, and put everything in your entity component system. So implement your engine, your game, your whatever, using the entity component system, try to do everything in your entity component system. Well, don't do that, because this isn't a great approach. The problem is that some problem can be solved with this approach, some others are just not good. And so if you try to solve them in terms of components, entities, and system, you're just going to ruin performance. So you have to look at your problem, look at your data, and decide if using an entity component system and just solving your problem in terms of components and entities is a good idea. It's not necessarily a good idea. So the talk is about entity component system and how we can implement something that works. I'll show you 3 implementations. One is probably the most used in the C++ community, or at least it was. So the most used until some years ago. One is the simplified version of what Unity did in their engine, and one is an approach that is quite different from the others, but there is pros and cons. And I'll try to analyze also what are the pros and cons of the different approaches. This one is the most basic and quite straightforward to implement as an approach. It's the one used by itCppCon19, that is a C++ library available on GitHub. The basic idea is that here your entities are also your indexes. So you have a big array or a matrix, but you can imagine it as a big, if you have 3 components, you can imagine you have 3 arrays where you store your components. So one array for one array for input system, for input receiver component, one array for FSM, one array for position, and so on. And when you want to assign to an entity a component, you just go in the you can just use the entity as an index in the array. And so if you want to, here is immediately a problem. You don't know actually if an entity has a component or not, because look at the second line. When I assign, the example also, yeah, the second line. When I assign the component to entity 1, necessarily a component is created also for entity 0. Default constructed, and it's there, just in case, if I need it for entity 0. But I won't assign anytime soon this component to entity 0. So if I want to know if my entity 0 has or not the component, I have no idea, I have no way to know that. And therefore, usually in this approach, there is also all the entities, and there is also another array of bit sets or bit mask that tells you, okay, this entity has or not this component. And this also is a good thing to speed up during iteration. The next dias show what does it mean to iterate over this array. This is used to speed up iteration because usually when the array is really sparse, you don't have to load things from memory because you can just iterate over the bit mask and say, okay, this one, no, this one, no, this one, no, until you find something that matches the components, the mask you are looking for. What's the problem of this approach? Well, first of all, there are, if your metrics, your arrays are sparse, you're wasting a lot of memory. And you have also a lot of jumps, because actually when you want to iterate also only, as an example, I don't know, input receiver, you load you know that entity 0 as an input receiver, so you get the first element and you are receiving a lot of stuff that you're not going to use. So the more the jumps, the more the information, the data that you receive and you're not going to use, so they're only just to waste space and to ruin performance. And this is more or less the main problem. Another problem is that you are really wasting a lot of memory, because if there are a component, as an example, the first component, input receiver, that is assigned only to entity, I don't know, 100, you have 99 instances of these components, that are there, that are default constructed, and that are absolutely useless. And you're wasting memory for them, because you have a vector, and you're wasting memory to store them just in case. If someone, sooner or later, if entity 3 tomorrow decided it wants this component, it's there. And this is quite wasteful. To iterate entities and components, so imagine you have a system that wants to iterate all the components that have position and velocity. How does it work? It's quite simple. This is straightforward to implement, straightforward to understand. It's quite simple, actually, because it just starts iterating the array of bit sets, so the array of bit masks, and say, okay, first of all, it creates a mask, saying, okay, I want this bit and this bit it flips 2 bits in the bit mask, and then start iterating the bit set, so the array of bit mask, and looking for matches. So whenever an entity matches the mask we are looking for, we can go into our arrays and get the items. We are sure that these entities owns the components, and so we can return them to the caller, to the system. The problem is that you don't know, and this is one of the big problem of this approach, you don't know absolutely how many entities have the components you are looking for. So you have all the times you have to iterate all the entities. So all the systems, every frame, iterate all the entities, at least all the bit masks. And this, again, it's not that good for performance. So things are apparently tightly packed, but they are not actually, because of holes, and you are wasting a lot of memory, and you are wasting a lot of time iterating things when it would be much better if you knew in advance what are the entities you want to work with. So the big arrays is good enough. It's used in a lot of games, in a lot of software, not only games. Because it's really, really easy to implement. It's 2 hours or so, and you have a version up and running. Performance on construction and destruction are the best you can get. There doesn't exist another solution that has the same performance on construction and destruction of components, because on destruction, it's a matter of flipping a bit, while on construction, it's a matter of flipping a bit and initializing a component. So it's quite fast to create things. when components, when arrays, when you have more or less all the entities have all the components, it has pretty good performance, but also you don't need an entity component system. You don't need to use this approach if this is the case. So it doesn't make much sense to use an entity component system. And so it has good performance where you should not use it. So it doesn't make much sense. It wastes a lot of memory. And the more holes you have, the more the worse are the performance. So during iteration. So this is used for small games, but it's not the. We can do much better with other approaches. What are the approaches? This one is probably one of the best approaches ever. It's also a simplified version of what Unity does with its engine, the Unity engine. A really simplified approach. Really, really simplified approach. The basic idea, it's an archetype-based approach. And the basic idea is if an entity has a specific set of components, there exists somewhere an archetype that contains all the entities and all the components for this specific combination. So imagine you have 3 entities that has position, velocity, and sprite. And you have an archetype that contains all of them. When you add a new component to an entity or you remove a component from an entity, this entity and all its components, so the old one plus the new one, if you're adding a new component, are moved at once in a different archetype. So position, velocity, and sprite, there were 3 entities. I took the same component to entity 0, entity 1, and entity 2, and another component to entity 0. So 2 new archetypes have been created, and entities and their components have been moved in these archetypes. So first of all, it's quite obvious that creating and removing, adding and removing components isn't that good with this approach, because things are moved, but it would be good if only entities are moved, but here entities and components are moved around every time you add and remove something. So performance, in this case, so this approach isn't that good if you have very dynamic entities to which you attach and remove components at runtime every frame. It's not a matter if you work with a few entities, 10 or 100 entities, but you should start touching and removing components from 1,000 of entities each frame. It could be a problem. It has another problem that's the one of the fragmentation, because the more combinations you have, the higher is the fragmentation. What does it mean? That you have more and more and more and more archetypes. So this is really, really good when you have few archetypes, few combinations of components, and it's getting less good when you have many combinations of components, so the fragmentation goes up. On the other side, it's really, really multi-threading friendly. In particular, the block-based archetypes, that is what the Unity engine does. That is kind of, here you can imagine every archetype has, as an example, this one has 4 arrays. It puts components in these arrays. Block-based archetypes work slightly different. They have pages, and every page contains, I don't know, 5 entities with their components. Then they attach another page, and every page contains 5 entities and their components. Why this is good for multi-threading? Because literally they create a job for every page and put the jobs in a queue, and their job systems start working a page at a time. Because this version is good for multi-threading as well, but if you want to, as an example, iterate in parallel all the entities that have position, velocity, sprite, so you have some entities here, some entities here. You can say, okay, I give all the entities from an archetype to one job, and all the entities from another archetype to another job. This isn't that good if they are, if you have, as an example, only one entity in one archetype, and 1 million entities in another archetype, because one thread does nothing and the other is really has a lot of things to do. What does it happen when we want to iterate entities in this case? Imagine you want to iterate all the entities that have only the sprite component. You have to find or cache, if you prefer, if you know how to do that, if you find a way that works, the archetypes that have the entities that have at least the sprite component. This isn't that good. This is good. This is one of the best approach ever, but it's not perfect. And here we start, we understand why it's not perfect, because you don't have everything packed together, but you have your archetypes have all the entities that have a specific combination of components, but when you are looking for a combination of components, you have not a single archetype that contains all these entities. But there could exist more archetypes that contain entities that have at least the components you are looking for. So you have to iterate all the archetypes and search for the ones that match your query. And if they match your query, you can start iterating all the entities and all the components in this archetype, because you know that all the entities in this archetype has at least all the components you are looking for. So when you find the right archetype, it's good. You can go straight to the point, but you have to search these archetypes. So fragmentation introduces some jumps you would like to avoid. Remember that this approach is more or less all about reducing jumps in memory, so cache misses and things like that. And here you're jumping here and there because you don't know where are your entities. So it's not that good. You don't know in advance how many entities you are going to iterate. You can know that. So it's good, but it has its problem as well. Obviously, this isn't the preferred approach. Unfortunately, there doesn't exist a preferred approach in this field. It's fine where performance matters, so feel free to use it when you really need really good performance. It's really fast on single and multiple components, so iteration on single and multiple components. It's really multi-threading friendly, especially the version, the Unity version, so the one with pages, with the block-based version. It has the best performance ever in bulk creation. Bulk creation is when you say something like, I want to create 100 entities with these 3 components. And this is the best approach, where it has the best performance when you want to do bulk creation, because you can imagine, okay, you want this create entities with these 3 components. Okay, where is the right archetype? It finds the right archetypes and append everything at the end of the archetype. So it's only a matter of finding the right archetype, and then it's the best thing. In the other approach, if you remember, it has to find where is the right entity. Not at this, because you could have destroyed entities everywhere in your array. So it has to find where are the entities and could jump here and there in memory. In this case, you append everything to a block of memory. In the block-based approach, you create new pages and put everything within them. So it's really fast. Fragmentation is one of the problems of this approach. And that's why it's really good for low-level systems. So at the engine level, not that good for high-level systems, so gameplay, where you usually attach and remove things frequently, and you have a lot of combination, where in low-level systems, usually combinations are a few ones. And so this is probably the best approach. And another problem of this model is that some operations are not easy to implement. As an example, sorting, because you can imagine if you are working in painter mode, so as an example with SDL2, that the last thing you draw is at the top of the, is in front of everything else. And here you cannot sort things. So it depends on what you're doing. This approach could, you have to do sorting with another data structure that works aside the entity component system, so your repository or central registry. The third and last model is based on a data structure that is quite known, I guess. I think, I'm not that sure, but anyway, it's called sparse set or packet array, or it has a lot of names, but it has also interesting performance, in theory at least. How does it work? Imagine you want to use it to keep track of entities, and you want to use it to keep track of entities because this data structure is used in different models to implement entity component system. Sometimes it's used in within system, directly within system. Sometimes it's used in a central repository, and so as a pool of components. You can use this data structure in several ways to get there, but imagine you want to keep a track of an entity. As an example, entity 7. How does it work? You go in the sparse array at position 7, and you find there an index. You go in the internal array, it's packet array. The two names are packet array and sparse set, because it depends if you look at this data structure from the outer array. That is the sparse one, and therefore is a sparse set. If you look at it from the inner array, so in the dense array, that's because someone call it packet array. Anyway, if you want to know if an entity is part of the sparse set, entity 7, you go in position 7, you find an index in the sparse array, you go in the dense array, at the index you find in the sparse array. If there you find the entity you use to access the sparse array, then the entity is part of this data structure. Straightforward. It's really fast to make a check. You have two indirections, so you have a bit an indirection, so it's fast only in theory, but it's quite fast also in practice. When you want to iterate everything, so it doesn't matter if it contains something, I just want to iterate all the entities that are part of this data set, then it's really, really the best you can get, because you iterate the dense array and you get rid completely of the sparse array. And so in this case, it's really, really fast, because you start from position 0 and go to n with no jumps, no holds, with no problems at all. And so it's probably the best thing you can expect when you want to iterate the entities that are part of this data structure. How does it work when I want to add a new entity? I just push I want to add entity 6. I just push the entity at the back of the dense array, get the position, and put the position in the sparse array at the index identified by my entity. So to insert a new entity is really, really cheap. To destroy something is cheap as well. It can be expensive if you have things that are far from each other in the dense array, but still quite cheap. Imagine I want to get rid of the last entity, so entity 7. What should I do to do that? The idea is that this array cannot contain holes, so I cannot just remove the entity 7 and leave an holes at position 1, but I can swap these two elements. So 7 and 6, I can swap the two elements and update the element in the sparse array. What elements? The one for entity 6. Why not the one for entity 7? Because of how it works. The idea is that when I arrive with the entity 7, I want to know if the sparse set contains entity 7. I go in the sparse array. I find the index 1. I use it to look in the dense array. I find that at position 1, there is entity 6. And it means that entity 7 isn't part of this array. So this is, there is no, I can just, leave the element in the sparse array as it is and not to update it. Also, I wouldn't know what to put there, so who cares? This model is used in several ways. There is a library written by a guy that had some talks here in the Italian C++ conference, Vittorio Romeo. The library is called ECS. It's a bunch of templates, really well-written library, but really an amount of templates, an incredible amount of templates. And he uses sparse set to keep track of the entities directly within the system. So the idea is that system register themselves with a central repository, and the central, whenever something changes, they receive a notification like, hey, you were interested in the entities that entered the group component A, B, and C. This one just entered the group, so keep track of it. And the system has a sparse set internally, and just add the entity at the end of the set. When an entity exits the group, it's the same. It receives a notification, says, hey, this entity is no longer part of the group in which we are interested, and it removes the entity. So whenever you invoke update on the system, he knows exactly what are the entities on which he wants to work. And this is great, because this is the first case in which we have the entities to work, to use. In all the other implementation, we never had the whole list of entities to elaborate. In this case, we have the list of entities. Entity is another approach. It uses the sparse set within the pools. I obviously talk about entity because of reasons. It uses the sparse set within, to create pools of components, obviously. The dense array isn't a single array, but it has two arrays, one for the entities and one for the components. And whenever two entities, whenever you delete an entity and therefore swap to two entities, it swaps also the components, so the two arrays are in sync. One of the problems of this approach is the sparse array, because you are wasting some memory. The performance are really, really good. Imagine you want to iterate all the entities that has the component velocity. You just get the internal arrays, and you have no holes, no jumps, no problems at all. You just go onto pegged arrays, so performance are the best you can get. But to offer, and also creation and destruction of components are pretty has good performance, but this is a price, that is the external array, and entity in this case has pages for the external array, so to reduce the memory consumption. Actually, it's not that much. You can live without these pages in most of the cases, but it's a plus to reduce memory usage. This model offers some nice features. As an example, it supports multiple access patterns from linear access, obviously. So you want to iterate all the entities, and that's it. Here is your entity and your components, get it. When you want to iterate multiple components, there are two approaches. One is, as an example, I want to iterate all the entities that has both the component position and velocity. One approach is to get the two pools, find the shorter one, so the one that contains less entities, and start iterating this pool. And for every entity, for each entity, as to the other pool, do you contain also this entity? Because you know that that entity is a good candidate, but you're not sure that that entity has both a component, so you have to query the other pool. This has indirection, because this, oh, thank you. this goes through the sparse array. But this model supports also what is called perfect SOA. It is something invented by a user of entity. And the idea is that whenever an entity enters a group, so as an example, the group position and velocity, it's moved at the top of the internal arrays of the two pools. And you keep track of the next position where to move the entities. So when you decide then to iterate position and velocity, you know that all the entities are at the top of the arrays. So all the entities that have both the components are at the top of the arrays and are sorted the same. So you can go from 0 to n on both arrays without branches, without problems, without any jumps, without any holes. And this has probably the best performance you can imagine. The problem of perfect SOA is that you cannot apply it in any case, in all cases, so just something you have to decide to use on most critical paths, and all the other paths have to suffer from indirection. So grouping functionalities can reach outstanding performance, the best you can imagine, but are quite limited. And so users also usually use more registries, so they can use groups almost everywhere and reach outstanding performance, really good performance. Single components is the best you can imagine. And also when you are in perfect SOA mode, multiple components are the best performance you can imagine, are given by this model. Unfortunately, multiple components isn't something you can have for all the combinations. It's multi-threading friendly as the archetype-based one. Not as much as the archetype-based one, but quite multi-threading friendly. You have to do something more, but you can get there. This is why the archetype-based model tries to optimize everything, give you the best in all cases. This one can give you even more performance in some cases, but you have to know your data and what are your critical paths. So you can decide to create the right groups and get the best performance with perfect SOA, this approach, on the right paths. So you have a burden on you. There is a burden on you about where to create the right things. It's not as transparent as the other approach. Indirection can be a problem, but it can be refined, and this is the grouping functionalities to eliminate indirection in most cases, so who cares? On non-critical paths, indirection isn't a problem at all. So are they in the same ballpark? Absolutely. The big array is in the same ballpark. Archetype and sparse set are in the same ballpark, absolutely. You have the differences as less than 1 milliseconds on 1 million elements, usually, at least on the benchmark, as someone tries to do, but these benchmarks are also quite pointless, so we can just ignore them. What is important, because of their feature, of how they work, they are well suited for different part of your game. Especially archetypes are good for low-level system where things change not so much and where combinations are few ones. Otherwise, it has the problem that things are moved here and there and fragmentation goes up, and so you have some problems that are the typical problem of an archetype-based solution. Sparse set are a really good fit for gameplay level because they are really good when you want to attach and remove things on the fly, and this is something that usually happens at gameplay level. Anyway, both are just fine if you want to go full ECS. That is, if you want to use an ECS both at low level and at high level, and so offer to the final user a way to work with components. You can just get one of the solution, and who cares? It's important to know it's important to know to consider the way you want to create things. If you are going to create entities and components, use much bulk creation, archetypes are the way to go, especially if you have few creation destruction on the fly for components, because they suffer from the fact that they move everything from an archetype to the other. While sparse sets are really good because of the fact that you can create and destroy things really, really fast, are good to do more and more things in the entity component system. So you can move your messaging stuff, so your messages within the entity component system, your input layer within the entity component system, and move more and more things that requires to create and destroy components on the fly each frame within the entity component system. Well, you cannot do that with archetypes because it will suffer from the problem of moving stuff around. Another interesting feature is that sparse set always offers a T-star size, so a pointer plus a size for every component. So here is your component, and here is the number of things you can find from this pointer on. While archetypes cannot offer this thing, this sounds like something that isn't important, but it hides something that is important. It is that with sparse set, it's easier to define custom allocators if you ever need them. Because in the other case, allocators are for pages, for archetypes, but a per component allocator isn't that easy to define. While with sparse set, you can easily define a per component allocator. And also, sparse set supports sorting and things like this one out of the box, so they are really good. Finally, a bit of C++. Entity is an open source library. It's on GitHub, so you can look at it. The last slide contains some links. The arrow in there, right? If you are interested in C++, a lot of templates, some optimization here and there, and a lot of stuff. Here is what you can find in this library, and by the time it's over, so I cannot go in details with all these things. And so that's all. Oh, if you have any questions.